working on in the lab for the past, I would say, maybe 5 years. And the research itself evolved during the past 5 years to very interesting directions. I would like to especially thank my past PhD student, Hussein Jalili, who actually did this research from the beginning. And I really enjoyed working with him towards the whole process. So what I'm basically presenting is the summary of his 5 years of very hard work and dedication to this project, which resulted in a really interesting results, which I'm going to share with you guys. The concept here is to use traveling wave and standing wave properties to achieve different properties and different performances for terahertz and millimeter wave frequencies. These systems are basically power generators, radiators, beam steering systems, and at the end, I will also talk about the reconfigurable arrays. So this is the outline of the talk. I would like to first go into a very quick introduction on why are we interested in these high frequencies. And then I will talk about 3 blocks, 3 systems that we implemented. The first one is a phased array, a 340 gigahertz phased array, which uses a new concept to steer the beam. The next part of the talk, excuse me. So the next part of the talk is about radiator arrays. No phase shifting, no steering, but we focus on optimizing the directivity and the EIRP for high frequency operation when lens is involved. And then the last part of the talk, we basically take advantage of those 2 blocks that we just presented, which is a steering, the steering angle, basically the phase array, and the lens-based radiator. We combine the properties and what we actually learn from these 2 blocks, and we basically implement a reconfigurable 450 gigahertz array or phased array with steering capabilities. So the first question always is, why do you want to go high frequencies? I think this is, at least now, it's easy to answer that question, and everybody is now exposed to this question since the 5G and all those new technologies that high frequencies comes into play. So these days, I don't really have to focus on this anymore because everybody have the sense of why high frequency is important. Of course, the bandwidth is the main objective here and the main benefit of high frequencies. And that's why most people go to those high frequencies. But there are other properties too. For example, you have more free space traveling loss, and then that will cause less interference. It also causes isolation between different transmitters. With all of these can be good or bad, but when you're looking at communication or IoT systems, these are all good stuff because you kind of make systems isolated if they're apart with some minimum distance. And then at these frequencies, you also have very interesting signatures. Like, for example, these frequencies pass through clouds, smoke, and that's why you see these scanners in the airport that uses millimeter wave, so it can pass through the clothes and luggage and basically detect metallic object. The other very important property of high frequency operation is the size. For example, if you look at the antenna size, for example, in this picture, on the left side, you have an iPhone antenna, and that iPhone uses a 2 gigahertz carrier, and you see that the antenna should go all around the phone to be able to have enough directivity and gain. On the right side, however, you see one of our chips that uses patch antennas, and the frequency is 370 gigahertz, right? Orders of magnitude higher than 2 gigahertz. And you clearly see that the size of the antennas has gone down significantly. So the size is an important concept, especially today when we are talking about IoT systems and small sensors and all those things. So this size will come into the picture a lot. But of course, there are challenges. In fact, there are many challenges working at higher frequencies. I mean, the first and foremost challenge is the Fmax of the transistors, the gain of the transistors, basically, or what I like to call it, the activity of the transistors will get a hit when you go to very high frequencies. For example, in this transistor, you have an Fmax of almost 200 gigahertz. The very popular transistor is 130 nanometer HPT, but the frequency is limited. So people, if they want to generate higher than 200 gigahertz, they have to use harmonic oscillators to go beyond Fmax. And then when you do that, the total power generated by the transistor will go down. So then you have to go to array structures. And there you have different problems. And one of those problems when you want to put oscillators together to make an array is coupling network, the loss of the coupling network. This is something that we witnessed when we were doing the project, and then we tried to solve it. That basically degrades the power generation and operating frequency, all these parasitics in the coupling network. The other problem is, of course, bad actors and tunability at those frequencies, because when you go high frequencies, the Q, or the quality factor of the bad actors, will drop significantly. And then things really go south from there on, because you can't really change the frequency anymore. And the last challenge I want to focus on is the high power consumption when we are basically trying to implement phased arrays with beam steering and high directivity, which basically means you need to put more oscillators and more antennas and couple them together. And when you do that, you have to burn more power to get the directivity that you want. So this is also a challenge, because you really can't burn power as much as you can. It's just the reality of the electronics. You have to limit the power consumption to be able to make the systems realistic. So given all this, I would like to first focus on the first block that we implemented, having all these limitations in mind. So let me first talk about the high-level understanding of what the idea is. If you look at, again, the idea is having arrays to be able to get over some of those challenges that I just talked about. And for that, we focused on standing wave properties, and we tried to use standing wave structures to be able to have arrays which are scalable. In other words, instead of just putting different transistors and connect them using coupling circuitry, we were thinking of basically having a unistructure that all of it, like the whole array, is oscillating together, not just individual parts that are coupled using extra components together. And this way, we can solve that coupling problem, and we can also solve the scalability problem in that regard. We also use a tunability technique here that avoids bad actor, which only uses the biasing to change the frequency. So if you want to look at it graphically, this is what people use conventionally. All these small blocks over here are oscillators. And these arrows over here, they're basically coupling circuitry. So you always have to have some coupling circuitry that is connected to the oscillator, and just you're coupling it to the Jensen oscillator. And that way you basically have a radiator array. But what we are looking at is a unistructure, a complete structure that has multiple antennas connected to different parts of this structure, and the whole structure actually works together. And this way we avoid all those coupling elements. So before jumping into the systems, we first need to focus on the standing wave oscillator. What is a standing wave oscillator? How do we implement it here? So if you look at this top picture over here, it's a very simple structure to, if you think about it, it's just a transmission line is basically terminated on the left and right with large capacitor. And then you have two transistors on the top, which are connected to this transmission line. And basically what these transistors are doing, they're basically canceling the loss of the line. And then this way, you create traveling wave on this line, which goes to the right and left. And then when these two traveling lines add up, you create a standing wave like this, which has a node in the middle and has an antinode on the where the transistors are, and of course on the termination side you have a grounded signal. The good thing about this is that if the negative resistor that is generated by the transistors are narrow band, then you will make sure that when you connect multiple of these standing wave oscillators together, the frequency of oscillation doesn't change. To make that a little bit more clear, let's think about this standing wave oscillator that has a wideband resistor generation, or the wideband negative GM generator. If you take another one and copy one of this and just paste it together like this, then no guarantee that you will keep the same mode or the same frequency of oscillation, because now you can have multiple modes created on this line. So if you have a wideband negative resistor generated by the transistor, it's really hard to keep the frequency the same. So what we do, we want to make sure that the negative GM or the negative resistor is only created at certain frequency range that we care about, and we do not want to cover the harmonics of that frequency. It's not a very narrow band negative GM, but it's enough to make sure that the harmonics of that mode we are interested in cannot really sustain the oscillation. In that way, if you do it that way, then if you take the same transistor, the same unit cell oscillator, and just connect it together like this, then you just keep the same frequency. And you can just keep this, ideally, you can keep this going, right? So you can just connect them together and you keep the frequency the same, but you actually can multiply the number of oscillators that are coupled to each other. So we got this concept, and then we basically put it in an actual chip oscillator, in an actual implemented oscillator. What you see here on the top is basically one unit cell of that standing wave oscillator. You're familiar with the bottom part here. We just took one bottom part and just copied on the top side. So you will create a differential oscillator, which are coupled together through their drain. So we basically have a larger, more transistors connected to this structure and to this antenna, which is connected to the middle point, and basically increase the power that is radiated through this antenna. So just keep that unit oscillator in mind, because we are going to use this over and over until the end of the talk. And this is something that is the block diagram, or it's a building block of all the components we are going to work on. So for example, here, we just connected 4 of these together right next to each other. We don't really need to change it. We just need to remove these capacitors on the boundary here and just connect them all of them together, and only have terminations on the left and right side. And this way, again, the frequency doesn't change. You will couple them together. And now you have multiple antennas that are radiating a signal, which are all in phase because they're coupled together and the phase is the same. So they're all behaving like a radiator array, and all the signals are in phase. So we did implement this. I didn't want to go through the implementation here on this structure over here because of the time, but we did implement a 4-element radiator array here. And then the next project we worked on using the same unit cell was a 2x2 phased array. And the way that we implemented this is, again, we have this unit cell over here. And this unit cell has, again, 4 transistors, a patch antenna on the top. And we basically connected 4 of them in this order, as you can see here. It's one on the right side, and then the same copy on the top will be copied on the bottom. So this is basically the total, or the complete structure of a 2x2 phased array in this case. If you focus a little bit more on the biasings here, you notice that there is a base biasing over here, which is called VFR. VFR controls the base voltage of all the transistors. In other words, if you change VFR, that means you're changing the capacitor seen at the base of all these transistors, and basically, effectively, what you're doing is you're changing the frequency of operation. Another control voltage that you see is the emitters of the transistors in each unit cell. So for example, this unit cell has an emitter voltage VST1. This unit cell has an emitter voltage of VST2, and so on. So these four biasings, or these four control voltages connected to the emitters, will help us to steer the beam in this situation, and I will discuss this later. So again, this is the routings of VFR, which is the frequency change of the array. And these are all the VST voltages which are connected to the emitter voltages of each unit cell in this structure. So let's, to understand how the steering here works. And first of all of them are connected together and coupled together. So if everything is symmetric, you have a very good radiator array where all the signals radiated from all these patch antennas are in phase. But now we want to focus on this part of the array to understand how the steering works. So this is the blow-up version of that bottom part. You see this transmission line here. You see the two bottom side of the unit cell oscillators. And you see this VBEs, like the base emitter voltages of this unit cell and the base emitter voltage of this unit cell. If the VST voltages here in these two scenarios, in these two unit cells are the same, that means the VBE voltages are the same. So again, everything's symmetric. You have this nice standing wave signal on the transmission line, and this antenna and this antenna will radiate in phase, and you have a very nice 0-degree radiator. But then if you start to change the VSTs, for example, if you create a delta VST between a difference VST, basically between VST1 and VST2, you're effectively changing the VBE of this unit compared to the VBE of this unit cell. That basically means you are generating more power on the left side, on the left unit cell, because VBE has gone up, compared to the unit cell on the right side. And that kind of makes everything asymmetric, right? It's not symmetric anymore. But because you are generating more power on the left side, you see a traveling wave that travels from the left side to the right side, because it wants to basically send the power to the right side to compensate for the lack of power that is generated on the right side. And that's why effectively you will see a standing wave which has a traveling wave on top of it. How does that look? On the vector side, if you look at it, you have a standing wave, for example, here, and then you have a little bit of traveling wave over here. So when you add them in a vector domain, you see a little bit of change in the phase. The same thing for this transistor, and this transistor. And when you combine all these phase shifts, you see that the phase of the signal that is generated by this antenna and this antenna, they're going to be out of phase. And then you see a nice steering between the two antennas happening in this case. So we use this concept, and we implemented the same 2x2 phase array. This is the measurement results. Without any phase shifting, we get a 15% tuning range from 318 to 370 gigahertz. Because of the standing wave properties, we don't lose that much power when we are changing the frequency. I don't have time to go over the details of why this is happening, but this is a very nice concept in the standing wave oscillators, that when you change the frequency using the base biases over here, you don't lose that much power compared to other works. So here we only lost 6 dB of power over 50 gigahertz of tuning range. So now we steered the beam. So from the right side and the left side, we change the VST voltages with respect to each other, and then you clearly see that we have steered the beam to the right and to the left. This is the E-plane, which is in the X direction. And then we were able to basically have 128 degrees of beam steering at 350 gigahertz, which is still a record at these frequency range for on-chip phased arrays. And the other good thing that we were interested in was how much frequency is actually changed when you're changing these biasings with respect to each other. And that basically shows here that they basically compensate each other. So the right one and the left one, when you change the biasing voltages, one of them have a higher frequency, natural frequency, the other one has a lower natural frequency. When they couple to each other, you see that the frequency stays in the middle. And this is a good thing because you can actually use PLL to easily lock these to any frequency that you like. This is steering in the Y direction or H plane. We changed the VST on the top and bottom. Again, you see a good steering, but it's not as good. It's just 53 degrees. It's not as good as the X direction because this direction doesn't take advantage of the traveling wave concept and the standing wave concept, because that direction is only works on the injection locking scenario, which you are probably familiar with. So this is just a comparison table. This table is a little old, but it shows that the steering angle that we achieved is much higher than other works, and it's still, I believe, still the 128 degrees still is the record for steering angle for at these frequency ranges. All right, so this is a phased array. Let's change the direction a little bit and talk about radiator arrays, where we do care about EIRP and directivities there. The first question is, why do we even need radiator arrays? And it goes back to the EIRP, to the equivalent isotropic radiated power, which is a function of the power radiated and the gain of the antennas that are connected to each other. So we can increase both the power and directivity, and that's why people use arrays, because when you use arrays, you increase the power that is radiated, and because you have multiple antennas now back to back, you will also increase the directivity, or ideally you would like to increase the directivity if actually that happens. We will talk about that a little bit. So so this is basically the concept. You have multiple antennas, you have a coupling scenario, and you want to actually couple all these antennas as much as you can in a scalable fashion, right? How can you do that? How can you basically have this nice array that you can just increase the size as much as you want without paying too much penalty? So before, as you saw in the phased array, we used a patch antenna. A patch antenna is a very simple antenna to implement. However, there are some problems with the patch antenna. For example, the bandwidth of the patch antenna is limited, and the directivity is also limited. So what we would like to do, we would like to get some gain on the antenna side. So we basically changed the antenna from the patch antenna to a slot antenna, which is basically a backside radiator, and you can also increase the directivity of that kind of antenna using a lens. So with that combination, a slot antenna and a lens, we basically increase the directivity and we increase the bandwidth of the antenna at the same time. So with that kind of antenna, this is how the unit cell would look like. Again, it's very similar to what you just saw in the phase array. However, here you see a CMOS transistor instead of the BJT transistors, but everything else is almost the same. The transmission line, transistors, all these connections from the top and bottom, and of course in the middle, we have this antenna. This is the actual implemented shape of the unit cell. This line is a transmission line, is this green transmission line on the bottom, and this top one is this transmission line. This is the middle point, and this is the slot antenna that radiates the fourth harmonic of the oscillator through the lens and through the substrate. This is a more detailed version of that unit cell. It shows that for terminations, we use a bottom plate that creates a very large plate-to-plate capacitor, which helps us a lot when we are trying to make this node a virtual ground in this scenario. So how do we couple these unit cells together? What is the best way to do that? Of course, like what we saw before, we can just put them right back to back and just continue and go over and increase the size. The problem in that case is we lose that nice standing wave situation because of the phase shifts you get from these oscillators. So we had to come up with another way of connecting these unit cells together. And this is one of the ways that we found out will result in a very nice standing wave shape on these lines, because we are not really increasing the size of the line. We are just multiplying them in different parts. So for example, in the top line, you see two of these units that are connected. But then instead of connecting the same on the bottom, we just connect half of this line to the left side, to the right unit cell, and then connect the half of it to another unit cell, and we just go like that. So this way, we are not creating more than 2 lambda of lines for each unit cell, which makes it much more reliable to work with. So if you think about it this way, this is going to be an array scaling on the x direction. So we can just multiply these as much as we want without changing anything in the array. Basically, literally, we don't change anything. We just multiply them and we just increase the number of antennas, which is very convenient in this case. But then this is a 1D array, right? This is just 1D extension. What about the other row? How do we couple this row to the next row? And this is what we actually came up with. Again, there's a line that one half of it is connected to one of these unit cells. The other half, instead of going up, it will go down. I will connect it to another half of the line, and this line will go to the left side, and you can just do the exact same thing you did on the top line on the bottom side. And you just can go all the way to the left and then couple to that another row and all the way to the right and just keep doing it. This way, you basically can have any number of array size on the x and y direction without paying any penalty on the coupling circuitry or on losing the standing wave phase relationship that you so much care about. You have all of that simply just by using this kind of coupling scheme. This is the actual implemented coupling scheme. Again, the red line is one line and the yellow line is also another line. And these unit cells are basically coupling the green lines and the yellow lines together to create that kind of coherency between these antennas. This is the total implemented array. Using this structure, again, we used all these unit cells, like we have 6 unit cells on the top. These unit cells on the corner are the hinge cells. Basically, they're coupled. What they're doing, they're coupling the top row to the bottom row. So we need one here, we need one here, we need one here, and on the end, at the end of these lines, you see that we just don't want to connect it to anything else. So here we're just connecting only 2 transistors to the antenna, which also works in this scenario and this situation. So this is the coupling scheme. Let's look at the on-chip antenna when we are coupling it with the silicon lens. This setup that you see is basically just one slot antenna, which is connected and which is coupled to a lens through a silicon substrate in the middle. And when you look at from the left, this is the chip, this is the silicon extension between the chip and the lens, and this is the lens. And we wanted to basically look at it in the more details to see how the radiation changes with different parameters on the lens integration. So this is the bandwidth. This is basically the S11 of the antenna. And you clearly see that we get a much higher bandwidth compared to a patch antenna at the same frequency range. We get almost 82 gigahertz of bandwidth in the S11 side, from 400 to 485 gigahertz, which is significant. On the left side, you see the directivity, the gain of the antenna, and the efficiency. The gain of the antenna over here is almost 25 dB when you go all the way from 430 to 480 gigahertz. However, this gain is a very strong function of this extension, this silicon substrate extension layer that you put between the chip and the lens. And this simulation very clearly shows that situation. On the top side, you see only 15 dB of gain for the antenna when you only have 150 micrometer of extension. But if you make that extension 10 times longer, that's 100 thicker basically, you get 29 or almost 30 dB of gain. So you see how sensitive and how much this directivity is a function of that extension thickness. So this graph very clearly shows that. So you increase the extension layer from left to right, and you see the directivity peaks at the optimum extension length. The other thing that we did was we also increased the size of the lens, the radius of the lens. And when you increase the radius of the lens, the maximum gain also changes. For the larger lens, you get larger directivity for the antenna. So this is only for one antenna, right? Let's see what happens when you put that big array that I just showed you, the 22 element array. What happens to directivity? That's basically the question. Here, the simulation, we only use the 4x4 array just to make sure that we can actually do it on the simulation. And you see the simulation on the right as a function of different extension layers that you put for the wafer between the lens and the antenna array. There, you also see an increase in the directivity, right? From the left to right, you can very much see in both E-plane and H-plane that you get a better shape of the antenna when you increase the extension layer. So this is the simulation results for the maximum directivity when you use a 4x4 array and increase the extension length. You see there is an area, or there is some values of extension length that you get the maximum, and then you roll down on the left and right side of that extension length. And one interesting thing happens here, and is that this red curve over here shows the single antenna with the lens, right? And you see a very sharp increase to 30 dB of gain at that optimum extension length. But then you expect that if you put 16 of them, like 4x4 array, back to back, you expect that the gain, the directivity, increases by 10 log of 16, which is 12 dB. So you expect that the gain goes all the way to 43 dB of gain, but that actually never happens. You see that the gain, the directivity we get from a 4x4 array is in the range of 20 dB. And that kind of, it was, at the beginning, it was very strange to us. Why is that the case? And then when we looked more into it, we found out what the problem is. So I would like you to pay attention to this slide, because I'm going to use the same concept here in the last block that I'm going to talk about. So here you see two antennas which are displaced. One is a little bit on the right side. The other one is a little bit on the top. So one is here, one is on the top. You see that when you change the location of the antenna with respect to the center of the lens, the direction of the very narrow beam of that center of that antenna, or that on that beam, will rotate from the center. So it is not in the middle anymore. It is actually rotated to the left side. The same thing for this direction. If you go up, you also rotate in the H-plane a little bit. So just think about it. If you have an array of antenna, which all of them are basically displaced with different directions with respect to the center of the lens, then you see all these different patterns from each antenna just going to different directions, right? So it explains why when you put a lens for an array of antenna, you don't really see a 10 log of 16 increase in your gain, because they're not all in the same direction. They're in different directions, and that's why you see a drop in the directivity. Yeah, so this is I already showed that happens. And Here we show that basically one way to get around that problem is to change the size of the lens. Because when you change the size of the lens, what happens is you're basically changing the relative displacement of each antenna, which means you have that the change of the location of the antennas in the array has less effect on change of the direction. And that way we basically can bring all these different patterns, different lobes of each individual antennas closer together and increase the directivity. And this simulation kind of shows that happens. The green one is for a 4mm lens, and the blue one is for the 6mm lens. So it clearly shows that the directivity is actually going higher and higher when the size of the antenna increases. So we could increase the size even more. We basically couldn't do it in the simulator for more than this size. It was impossible for us to simulate that size of a lens. But we expect that the directivity will increase as the lens size increase. So having said all of that, we actually implemented this. Again, the same shape that I just showed you, 22 elements array in a 65 nanometer CMOS process. This is the way that we actually measured it. We had different wafers going between the chip and the lens, and we basically tried different thicknesses of the wafer to make sure that we have the optimum size for that extension length. And this is the first simulation results. This basically compares the directivity of the transmitter or the radiator array for different lens sizes. One is a 5mm one, the other one is a 12mm one. You clearly see that the directivity from the 12mm one has increased significantly compared to the 5mm, verifying what we saw in the simulation. This is the EIRP and frequency measurements. The EIRP we could achieve using the 12mm lens was very close to 20 dBm. And the frequency, again, we changed the biasings of the transistors, and we could actually sweep the frequency all the way from 480 to 400 and almost 440 gigahertz. So it was a significant tuning range for this array. And the blue one is also the EIRP for the 5mm lens, again showing that larger lens will help us with the EIRP and directivity at the same time. So this is basically the comparison table with the state of the art. This work on the top is our work. We could achieve 19 dBm of EIRP at 460 gigahertz. This is the highest EIRP at this frequency range. There are higher EIRPs here, but they're at lower frequencies. So with all those optimization of the lens size, lens extension, length, and all those simulations we were able to find the place and the sizes that actually optimizes the EIRP for us. The tuning range is almost 9% at 460 gigahertz. I believe the other one that beats it's 15%, which is our own work, which I just showed. It's a 2x2 phased array that I just mentioned. All right. So think about these two blocks a little bit. And in the first one, we used basically phase shifts. In the first one, in this phased array, the 346, we used coupling, standing wave couplings, and the phase shifts to basically steer the beam in a very efficient way, very nice steering mechanism, very stable. On the second one, we basically investigated the displacements of the antennas, and we studied how the displacements will shift the direction of the beam to different directions. So in the next project, in the last project I want to talk about, we actually combined these two effects to achieve something interesting, some array that can be reconfigured. We can reconfigure it and we can use it to also steer the beam to different directions with very good resolution for especially imaging applications. So let's take a look at imaging in general. So in imaging, you have a transmitter on the left, you have a receiver on the right, and you have a lens to basically make sure that you're illuminating a specific part of the object between the two lenses. One of the things that you required from the transmitter to do is to steer the beam. You need to steer the beam to the different parts of this lens so that the different part of the object will be illuminated, and then the receiver side will get the data from those different parts of the object. On this right side, you basically see the same thing. So you have a scan range, and the more resolution you have on the beam steering, the more resolution you have on selecting a different part of the object to illuminate, right? So this is something that you can use in the imaging, especially at those high frequencies for imaging application. So what is it that people use to actually steering the beam for transmitters? There are a few different ways of doing it. One is a very regular phased array situation, right? You have multiple antennas, you couple them together, and you're steering the beam that way, right? This way you do get high directivity, but to get high directivity, you need a very large array size, right? And that will cause a very high DC power consumption. Another way of doing it is to use a phased array with combination with lens. You basically have the same phased array and you just put a lens on top of it. So the experiment shows, the state of the art shows, there are few people that actually do this, but there are few works that actually has done that. They show that as soon as you put an array with conjunction of a phase array, you significantly limit the range of steering for the array. So you may get a better directivity, but you significantly limit the direction and the steering angle that you can achieve. The last thing that people use, this is a very popular way of doing the imaging at high frequencies, is just to use non-coherent array, which means you have multiple oscillators on the transmitter and you just turn on one of these oscillators at a time. And with that, you can basically send the beam to different directions. But of course, the problem is you have this discrete steps. So whichever you turn on, it has a very specific direction, and you can't really change the direction when you do the non-coherent array. So this is a summary for these different phased arrays. Without lens, if you have a phased array, you have a very nice continuous scanning. But of course, you have a very large power consumption, which is the cost of it. You also have a limiting scalability when you want to increase the scan range. So the scan range is a function of the phase shifters that you can implement, not the size of the antenna, not the size of the array, sorry. So when you lose lens with the phased array, you still can get a continuous scanning, but the problem is the scanning range. It goes down. The directivity also doesn't go up as much as you like. That's the problem. For the non-coherent array, you do get a scalable standing range, a scan range, which you can basically change the size of the array to increase the direction of the angle that you can send the power. It's efficient, it's directive, all of them is very good, but they're discrete. You can only send the power to a specific directions that way. And as we talk about, you will create blind spots. So the one that we are looking at is a reconfigurable array, which gives you an uninterrupted high directivity scan. It is scalable. You can change the direction, increase the angle of transmission, and it is also efficient and giving you a very low power consumption, as you will see. So let me remind you what happens when the antenna is displaced. So again, this is the center of the lens. If you change an antenna to the right and left, or right and bottom in this case, you change the direction of the antenna, you change the direction of the beam like this. So it is a good way of changing the direction of the antenna. And as I mentioned, in a non-coherent arrays, people actually do use this to send the power to different directions. Also, something I have to say is that direction is a function of the displacement with respect to the size of the lens. So the more the displacement, the more you will steer the beam coming out of the lens. So using that kind of method, you can clearly see, so this is a simulation and measurement results that we did for this array. So this is a 3x7. It's a 3x7 array. And we basically only turn on a specific component, specific oscillator and antenna on this array. And by just turning on different antennas, different oscillators, we can easily steer the beam to different directions, right? But you can clearly see that there are these blind spots between the arrays that you're not covering. You can see the problem here, right? You send this to illuminate an object for imaging, and you have absolutely no information from these locations of the object. So you do have a blind spot. To fix that problem, just think about it this way. So let's say you have two oscillators, A and B, right? We first turn on A, and we have a pattern to this direction. Then you turn on B, you turn off A and turn on B, the direction changes, right? And you can see that there's a blind spot between this array, this beam and this beam, which is here in the middle. What if we turn on both of these oscillators, A and B, together and use the same phase shifting mechanism that I just mentioned at the beginning of the talk to change the phase shift between A and B and cover that blind spot when you're doing the beam steering? If we do that, then we do cover the blind spot between the green and the blue, which is basically the individual beams from A and B. What do we get out of that? We get high resolution because you can basically illuminate anything, right? You can illuminate any part of the object. You get high directivity because you only have one or two turned on, so you get a very good directivity. You get a very good power consumption because you only turn on one or two oscillators at a time. And it is scalable because you can increase the size of this array and you can increase the field, the size of the object you can cover. You can increase the size of the object basically that you can cover. So putting all of these together, we would like to introduce this reconfigurable array plus the lens. So when you have these yellow ones, you get a very good direction, very good pattern to a specific direction. You change the phase between them and you change the direction right there. You can also turn different components, different antennas at the same time at different frequencies. So you have multiple beams which is on at different frequencies and they can operate at the same time. How do we do this? How do we turn on and off to basically make sure that they have a good coupling between each other, and then when only one of them are on, they're not loaded by different adjacent oscillator that is connected to the oscillator? So we use the same unit cell as you can see here, but we implement switches to the termination points here, and we also couple the unit cell using these capacitors to the left, right, top, and bottom oscillators. So basically, when the gate voltage of these transistors are turned off, we are basically turning on these oscillators and we are shorting the two sides of the oscillator. How does this work? Let's have two of these two unit cells right next to each other. Let's say we turn on the left one and we turn off the right side. So when we turn on this one, these switches are on and these switches on the right side are off. which means the termination on the right side for this unit cell is this capacitor, which is connected to ground already. So the loading, this unit cell over here does not load the on oscillator on the left side, which means it doesn't change the frequency operation that much, and it doesn't change the power, radiated power from this oscillator that much. And because this is off, it doesn't burn any power, and it also doesn't load any on oscillators that are connected to this one. What if both of them are on? Then these switches will turn off, which means this capacitor in the middle, which used to be the termination for this unit cell, now it's used to couple these two unit cells together. And now they're coupled together, they're in phase, and they can actually behave as a coherent array with two antennas. And as I mentioned before, you can use these two unit cells and change the biasings on the left and right to basically change the phase shift between these two unit cells and change the directions accordingly. So what about directivity? So again, you can, as I mentioned, you can have two antennas turn on at the same time. And if your extension length of the wafer is optimum for each antenna, that means you have a very narrow beam from A and B coming out. So you're here at the peak, you have the best directivity for each, and you get a very good directive beam from each of them. The problem is these two beams are not working together. They're not overlapped with each other. And that's why in that case, if you change the phase shift between A and B, you can't really get the steering. So we need to deviate a little bit from the top directivity. So these two A and B beams they do have a little bit of overlap with each other, so that when you change the phase shift between them, you can actually change the beam direction when both of them are on. So again, we have to deviate a little bit from the maximum directivity for each antenna to actually get that beam steering property that we need. So this is the array that we implemented. The unit cells over here, all those capacitors and everything are actually implemented here. This is the measurement setup. So this is the chip here, transmitter. This is the receiver side. And again, this is where the lens is. This is where the receiver is. This is the back side of the same setup over here. You see the chip and the wire bonding, everything happens here. This is the zoom version of it. Again, these are the setup, and we use spectrum analyzer and different things. And this is the harmonic hospice. The receiver is basically the harmonic mixer. So this is the frequency and power measurement results. Again, we could get a very good tuning range when we have two antennas coupled together or when only one of them are on. We get almost 7% tuning range for both cases, which is a good thing. It doesn't deviate. The frequency also for the specific gate voltage doesn't deviate much, which is also a good news when we want to use this in a system. And this is a power consumption graph, the measurement graph for different frequencies. You can clearly see that for one cell, let's say at the center frequency, we basically have a very reasonable power consumption. The range of the power is from 30 to 11 milliwatts. If we use two unit cells, a 1x2 array, then we see 45 by 138 milliwatt, which is also a very reasonable number when you compare to the state of the art. These are the directivity measurements in the X direction. Let's say we have two antennas turned on at the same time. We can cover all the way from 180 to 188 degrees. Now we turn off 24 and we turn on 26 to move the beams a little bit more to the right. So 25 is on, 26 is also on, so 24 is off now. Now we can cover from 188 to 198 with a very nice progressive direction of the beam going from 188 to 198. Now we turn off 25, we turn on 27. And we get, again, a very nice progression from 198 to 208. So you see a very nice progression all the way from the center to 208 degree of steering beam. You get the same thing in the Y direction, 188 to 181 to 188. We have only 3 units on the Y direction, and that's why we can only go to 188. If you can put more on the top, we can definitely get more steering that way. So this is the EIRP measurements. We get, when we use it 1/2, we get an EIRP of almost 4 dBm over here at 450 gigahertz. The one thing that is really good here is basically the directivity. So the directivity changes, I would say, although when you change the steering angle, the directivity changes from, I believe, 25 to 22, 23. So the change of directivity is minimal when we go all the way from 0 to 30 degrees of steering. So this is the comparison. Again, I would like to note here that the power consumption is the main achievement here for the given directivity. So we only consume 51 milliwatt of power for 26 dB of directivity, which is a very important parameter when you're dealing with imaging. And if you compare it to others at the same frequency, you see that this is the only work that gives you this much directivity, and on top of that gives you a continuous phase, a continuous beam steering at the same time. So in other words, you get a good directivity, and you also get a very good resolution of how much you want to change the direction of that very directive beam. And that's exactly what you get in this work, which also gives you a very good resolution on the imaging side. All right, so just to conclude, it is very important at terahertz systems to have a reconfigurable high directive signal generation and radiation. You also need steering at the same time to actually make these systems a reality in the near future. The different individual oscillators need to be connected together in a very smart way to be able to scale, to have a scalable array and have a good steering at the same time. We showed 3 blocks, a phased array. We also showed a 22-element high EIRP 450 gigahertz radiator array. And we also showed a reconfigurable array that helps us a lot in the imaging application. I would like to acknowledge all the students in the lab. They basically always do all the work. This specific work especially is done by Hussein Jalili. And also I would like to thank NSF, National Science Foundation, for supporting this work. All right, so these are